Alrighty, we are officially getting started. So, welcome back. I know you're all very happy to be here again for another enjoyable weekend with me listening to me talk. Hopefully not all listening to me talk. Anyway, so I'm going to start out with the topic of the Linux kernel. User mode, kernel mode, system call, interface, interrupts, signals, all that stuff. You know, this is really a crossover. Sometimes you get this in a systems programming course. And systems programming is generally done on Unix. So there's a little bit of information that will help you if you go on to take a systems class, if you haven't taken one yet. Or if you have taken a systems class, some of this stuff will look familiar. But I'm picking it from a Unix because this is a Unix operating system. Unix perspective. The kernel is the brains of the operation. Everybody knows that. If you've taken any sort of class in the subject area, they always talk about the kernel. It's usually the word, it's the US word for the core of the apple. It's kind of the kernel. It's in the middle. Which it really isn't in the middle. It's actually abstractly on the bottom. And then you have the user mode on the top of it, or around it, you should say. So there's many different interfaces to the kernel, so that abstraction actually kind of works well. So knowledge of it will help you understand how to program in C. It will also help you understand Linux and Unix environments, as well as designing high-performance applications, scripts, and all sorts of different things to work with. That's why we're looking at it. Part of the OS that contains code for, and if I were really giving you a complete list, this would be like 50 pages long. This is like one slide. What does it contain code for? Well, okay. Back up, put some things into categories. How about controlling processes? I'm going to talk about processes and threads today as well. It's always a lovely topic for Unix. Creation, termination, suspension. Kernel's got this thing called a PCB, process control block. It's a data structure that keeps track of, usually in the form of a hash table, sometimes a tree-ish kind of structure. It depends on how it's implemented. That contains a list of all of the processes that are in the system. Those processes are sent over to a CPU scheduler. Sometimes it's just called the scheduler. The scheduler runs the processes on the, using the CPU, but also using the resources of the computer. So it creates a memory address from, it requests and asks for a memory address from the memory manager, which is a memory management unit. From the memory management unit. It uses it and creates another data abstraction to create memory on the system. And then loads the process up into memory, it takes and creates a stack entry for each one of the executable activation records in the file, and then pops each one of the activation records off and executes it using the resources of the computer. All the programming for that is done in the kernel. So that's what the kernel's job is. Well, when it comes to processes. But that's only one aspect. It's also keeping track of what memory is belonging to which process and where the memory is being used, and is the memory used or is it not used? Is it garbage going to be reclaimed? Things of that nature, which is really the bullet point number 2 in terms of scheduling processes. Doing it fairly for execution of the CPU. Actually, the interesting thing is Unix isn't fair. Anything started and running by the kernel always is a higher priority. So Unix uses a priority system process numbering, and the higher the level of the process start point and the process ID, the lower the priority. So things at a 0 to 10, 15, 20, high priority. Things at a 6,000, 8,000 level, low priority. So if you take a look at just running certain commands that give us the processes like PS, well, we got one here. The PS command was at 10,541. That's a pretty high, low priority process. Even the bash cell was a little bit lower. It was at 8,586. We're pretty high in its structure. So those process IDs are really, there's a code to that in terms of what numbering system we're on. Because and none of the process IDs are duplicated. They're use an ID once and throw it away. Use an ID once and throw it away. We never run out of IDs because then we can go up to an unlimited number. And depending upon what priority we're working with, we could have different levels of fairness that's allocated. What do I mean by that? Well, the process control block could be stamped with a priority number that says I'm a kernel process or I'm a user mode process. and I'm just using those two as an example. Then when the process comes up, it gets more CPU time because it's not running a process and stopping it, and then running another one, or not stopping it, but running it to completion, and then taking it out of memory and running another one to completion, taking it out of memory. It doesn't do that. Instead, what it does is it interrupts, it stops. They also call it preemption. So most of our schedules are preemptive because then we get multiple processes running simultaneously. On most computer systems with one CPU at any time, you have one process running. That's the laws of physics. Only one instruction can run at one time. So you put two CPUs on there, then you have the capability of having two processes running at the same time. One of them's using this CPU, the other one's using that CPU. And then you have a faster system. Or if you're not going to put on multiple CPUs, which we didn't do in the old days, you make one CPU share its power among all the processes. You put priorities on it. Some of the processes are going to get more time than other ones will. They'll finish faster. But it's sort of like the concept of building a house. They don't spend time building the foundation, and the foundation is not complete. The house is never going to complete because everything they're sticking on top of the foundation isn't going to hold up. So you might as well just build the foundation first, which is going to be all the kernel level stuff, and then worry about the user level stuff later. So, yeah. Okay, so allocating memory for the execs of processes. This is an interesting command, actually, or interesting exec statement there. It's short, and most people go, oh, it's just an abbreviation for execute. No, it's actually a system call, and a system call creates a process and then runs the process. So it's kind of a loaded expression, actually. It's a system call and an abbreviation for execution. Allocating secondary memory for efficient storage and retrieval of data. That's also a consideration of the kernel. And then handling peripherals such as terminals, tape drives, CD-ROM drives, all that other stuff. Short list of parts of the kernel code. Kernel characteristics. Kernel only gets loaded in once. So you load it into memory and it runs until the system is turned off or crashes. So hopefully it won't crash. So then we have kernel modules. So it's here Linux or UNIX kernel modules. You build modules and you load it on after the kernel gets loaded. If you want more flexibility. Because what the kernel is it's the entire abstraction of the operating system in terms of the core functionality. So it's going to recognize the motherboard, it's going to recognize, or excuse me, the CPU and all the memory components and all of the other I/O ports and stuff on the board. And it's going to be designed to work with the hardware and interface with the hardware. And then it has a system call interface that comes up and interfaces with the user mode. So isn't it just like one thing you just load first and leave on? And then you have kernel modules that you load on top of it. Why? Because you don't want one kernel. The one kernel, we started out with one kernel. And then we ended up with microkernels that came after that. Because one kernel, you stuff everything in the kernel, and then someone buys a piece of brand new hardware. You buy another CD-ROM drive and you stuff it on the machine. Now what are you going to do? Nothing. It's not going to work. So if you break the functionality out, modularize it. So they're called modules because they're in modularized kernel. Small bits of pieces of code that do all the different functions. And then make the base system very small. And then you load all the modules on after the base system gets loaded. More flexibility, better ability to adjust for new hardware. You just add a kernel module. If something's broken, you just change the kernel module. Unload a module, load another module. We're not going to be loading and unloading modules because we'd have to actually build our own kernel in order to kind of work in that environment. And you'd have to have your own PC dedicated to do it. You're not going to be able to add. You could probably add a kernel module to the Amazon server. We'll see how that works. In fact, I might try it at the lunch break and see if it's going to work. But really isn't a programming course. If this were like a C programming course or an operating systems course in general, I would have you build kernel modules and load them and unload them. But for our particular design of this course, kind of goes beyond the scope a little bit, so we won't do that. But no, it's written in C and some assembly language. The kernel is all written in C as well. In fact, you can download the kernel source code for Ubuntu or for Debian. 2.4 or 2.6. 2.4 is a little bit easier because it's not as big. Download all the source code, unpack it, it's all tarred, untar it, and run some pre-built scripts that bring up menu config and a couple of other utilities. Pick what you want, press a button, select an option, and wait about 15 minutes or so, and you'll compile a new kernel and then load the kernel on your system. It's not too hard, actually. It's pretty easy. It's just you'd have to basically know how to compile something in order to make that work. So user programs will make use of the kernel services via the system call interface. So it provides its services transparently, theoretically, transparently. Not so transparent. I don't know. You can actually get a list of kernel modules, get a list of system call modules. You can rebuild your kernel to change your system call interface. So your system call interface, actually, there's another good point I want to make here, is basically another table. Kernel is full of data structures, which is why if you're going to build kernels, if you're going to modify Unix, you're probably going to want to have a data structures course, only because then you can learn the more efficient ways of designing these storage of all this information that the kernel is keeping track of. Because what you don't want is the kernel to slow the system down to make the system run as fast as possible. So if you keep a list of all the system calls and the ones you're going to allow the user to use, then you can put codes on it. Instead of passing information back and forth via strings and character sets and stuff, just send the numbers, send the codes back. And then link that to an interrupt table. It keeps track of interrupts that are received along with codes. And then have the interrupts work with the system call interface. And then you have it all working kind of seamlessly together, number matching and doing logic with which number goes with which call and which number. And then you use it for signal handling as well. And then you have what most modern day kernels are configured with. Numbering systems that all work together, and some consistency among different subsystems. So they're all kind of sort of related. Which brings us to the subsystem concept. So we have a file system, a process management system, and an input-output system, inter-process communication, memory management. So hopefully by the end of today you'll walk away going, maybe I should build my own operating system. It's pretty easy, actually. A lot of people do this with Linux. You can actually build your own embedded Linux kernel system and work with, make your own hardware and then make your own operating system, stick it on the hardware, and then sell your product, which is what people do today. That's how a lot of stuff works. If you're not going to do embedded Linux, you'll probably do embedded Android, maybe. Embedded Android's pretty popular right now. Or depending upon the processor, if it's an ARM or something, you'll do some other kind of pre-built kernel, Linux-based kind of system, or Unix-based kind of system, I should say. Not so hard, actually, because all you do is you write a bunch of drivers for the hardware, a load of drivers in the form of the modules, add them on, compile a kernel to basically work with the minimal needed. Add a file system on there if you need it. Most of these don't have file systems. Your microwave oven doesn't have a file system on it, but actually it doesn't really have a full operating system. Printers are more of a better example, actually, but a printer doesn't have a file system on it either. So your microwave oven is a C program, most likely, or assembly language program. It's simply, that could be written in C. Itsy bitsy little UC Linux kernel could be put on there with nothing more than one running program in a state machine that looks for input. It takes the input, and if the input button is the on button, it turns the microwave on. If it's the off button, it turns the off button, it turns the microwave off. So there's a driver that works with the membrane, the number pad, and then there's one that's going to work with a little LCD output, right? A little character module for that. Load the modules up in the kernel, and then ship your product out and watch it go on the store and watch people buy it in the store.
But they run like pretty old processes like 86 and 80, 85 or 86. So can you load kernel systems into those processes?
Are you talking about like Intel chips?
Yeah,
80, 86s, 80. Oh, of course. But we don't even have to go that much. Little ARM processors or DSP or something. Just a small itsy bitsy little cheap processor. Intel's expensive. You're not gonna put an Intel chip. You're not gonna build a whole 8086, 8080, whatever those old architectures. You're not gonna build like a PC architecture for it. You're gonna get yourself a board, and you're gonna solder a chip on it, and you're gonna put some I/O lines on there and connect it through some channel, to go to the LCD, to the membrane, and you're going to have an interface to the other hardware that's going to actually operate whatever unit is generally going to be shipped to you from an OEM perspective, from whoever's manufacturing the inside. I don't know anything about operator. I don't know anything about microwaves, but I'm going to say there's probably a controller on there. Yeah. So there's probably a controller that's going to work with all the door and everything else, right? So you hook the controller up to the board, and then you read the signals from the controller that's going to come back and say it's done, so it can make a sound go beep, you know. Some of that stuff's probably on the controller already. I'm talking about, or my example is just on that little interface you got with the membrane and the LCD and the controller, which you can easily do. You don't actually have to, it's probably overkill. You don't even have to do that. But if you wanted to, you could put that into a, you know, more of a computer operating system kind of perspective and say, well, that's how the kernel would be built if you're going to build a kernel for it. Parnix, they have little baby kernels. Could be something more along the lines of, I don't know if you'd do it for microwave. Probably wouldn't. You'd do it for a printer. A printer would have one. Because what does a printer do? It's going to communicate with the network. It's going to need more functionality. So it might be a scanner, printer, fax machine. It might have some other functionality too. So the more sophisticated the product, the more of a kernel is probably going to be needed for it versus some embedded system that's just going to run C code or something from a, you know, from a special language of C kind of interpreter that's going to make it work. So it might be interesting to toy around with those little breadboards. I think they used to call them breadboards. You buy them in kits and it has a processor on it, has a USB ports on it normally. So sometimes you get them real small. You can put them in like little robots and stuff. They sell them at Fry's actually. And they sell them on the internet. Build your own vacuum cleaner, robot vacuum cleaner kind of thing. And usually there's a language, there's an operating system already on the device, and then there's a language that you're going to build the program in, C dialect of some sort, and then you're going to burn it on the board. Well, take it through a serial port or USB to serial interface, and copy the file onto the system board. Reboot the sucker and watch it vacuum the floor, or do whatever it's going to do. Those kits are kind of fun for kids. But the funny thing is I don't know too many kids that can handle it. It's like they make them for the kids, but only like a certain percentage of, well, kids in the U.S., only a certain percentage of them go to actually have the patience for it. And then the adults, they think, oh, it's for kids. But it's actually kind of fun as an adult to play with those kits because it's like, wow, and a kid's supposed to do this? You know? And I have to solder it? Some of those kits require you to solder. And I usually, you know, starting out, I had really bad soldering skills because I didn't take a class in soldering. But how are you going to solder the little wires on the bottom of the LCD to a control board? Or how are you going to fix something on the, add a battery to the control board or do something, unless you know how to solder? And I'm thinking, so I bought one of those kits, and it was a solder kit. And it took me like 10 times to get the thing to work. I kept having to melt off the silver stuff and try it again. And finally I wore it out, so I had to go buy another kit once I learned what I was doing to actually make it work. And it was still kind of faulty. Then I learned I'm not a solderer. You have to have like really, it's like you have to be an artist almost. I mean, you have to have really, but then I found the key. I found the trick to it. And I didn't find the trick to it until I was interfacing with somebody else who does soldering for a living. Part of her job was she was making some soldering stuff. They make these really huge mirrors, magnifying glasses. There's a magnifying system. I wasn't using that. So you put the magnifying over the solder area, and now it's huge. Now you put the little dab, and you can just put a little dab. You don't have to, and then depending upon what kind of gun, I was using the wrong gun. There's better guns out there. And I'm thinking, oh, now, if I knew what I was doing, then, you know. Anyway, long story short, the value of that lesson is money. The more money you spend on the toy, if I had bought all the equipment I needed for it, I would have been able to do it no problem. So, but I'm kind of glad I sort of learned how to solder. I don't think I could solder to save my life, though. So, it's not one of my core competencies. So, you guys know how to solder? You guys ever try soldering? Yeah. You tried soldering? Are you good? Yeah. Use the big magnifying glass?
Yeah, I used to have one. I
Oh, yes, they have them put it in the eye. This one, the one I actually bought one of these suckers. The one I have is a huge magnifying. You stick it over so you just look into it. Because, or you can adjust it. It goes in a table unit, so you stick it on the table unit. It has all the protective stuff so you don't burn yourself, stuff like that. And there's like a little gun that has a special fine tip on it. And it heats up automatically for you and good and puts. It's like a $2,000 system. So I could play with a robot. Yeah, they don't teach it here. There's a value in learning how the components work. But we have a computer engineering department. And we have a computer lab, engineering lab. So maybe they're doing stuff like that. I don't know. It's in the U.S. It's very low tech, technical training. You go to technical college for it. You know, it's not a high paying job. It's manual labor. But from a computer science perspective, it's nice to know how the electronics work and how the power system works and all that other stuff and how the lines are done, just because it helps you understand the bigger picture. And it actually relates to kernels, because you don't understand what hardware is on the system. How are you going to write a kernel module for it? Or how are you going to write a driver for it? And then you're not getting the inputs and the outputs from where it's going to, stuff like that. It helps your understanding. So process management, input, output, interprocess communication, and management, memory management, also part of what the kernel does. Talking to the kernel, as I mentioned before, it's a system called interfaces. So from a user perspective, you got that down. And the reason I was mentioning soldering and hardware was because that's the hardware interrupt level. So from the hardware up, you have to build software that understands the hardware. So if you don't know what the hardware is, it's very hard to understand what you're supposed to build to work with it. So it's kind of like, yeah, you don't necessarily have to know how it's put together, although it does sort of sometimes help. You're thinking, well, why in the world would that help? If the I/O lines are kind of narrow, not so much bandwidth between something, are you really going to overwork that area of the processing? Are you going to really have it go? Or you know that, as an example, this is a no-brainer one. Main memory is pretty close to CPU. Cache memory is pretty close to CPU. Hard drive, not so close. Hard drive is very far away from the CPU, normally. And well, it doesn't even matter where it sits in proximity. It's the channel, getting to the I/O channel, going back and forth between it. So you're not going to write a memory management unit that does a lot of swapping. The more swapping you do, the slower the system's going to run. And that's an interrupt thing that you're going to work with. So when the memory fills up, how do you know how much memory to put on the sucker? And then most computer users go, well, I got to stick 8 gigs on my system. Older systems that had a lot of memory actually ran slower than some of the older systems that had fewer banks of memory on there, because operating systems didn't take that into consideration correctly. So you put 1 gig in there. All right, you got 1 gig of RAM in your system. Operating system isn't going to use just that 1 gig. It's going to make 10 gigs out of it. Or let's make a ratio here. Let's just double it. It makes virtual memory out of it. So we got 2 gigs. So at only one moment at a time, only 1 gig can fill up. But we're going to fill it up to 2 gigs because we're going to swap it back and forth because we're the operating system. Because we can't run the entire operating system in the user mode on 1 gig. It's not going to be enough. We can't even do it on 8 gigs for that matter. So older systems just doubled it. I'm just using this as a ratio. They didn't double it. There's another calculation you do on it. But so you put 8 gigs in there. Now you got 16 gigs of virtual memory. Let's say you're only using 1 gig. So you got 16 gigs of memory out there. That's all taking up memory of your 1 gig. At a certain point, the memory management unit makes an extremely inefficient use of your memory, fills it all up with all this need because it thinks you're going to need all this memory, makes the virtual memory abstraction, occupies your physical memory that you have. Long story short, you get to run slower because you're doing more swapping, because your programs can't fit, because the memory manager is preparing for something bigger and better. But you're only going to a certain point. Anyway, it's more overhead is the point I'm trying to make. For the memory manager, the more memory you put in there, the more overhead. If you're not using it, it's counterintuitive. It's not needed. Most modern operating systems have corrected that problem, however, by building a better memory management unit. Excuse me, a better memory management program. So, the other thing too is that the other misconception from a hardware perspective, because I keep saying memory management unit for some reason today. It's a hardware component. It sits on the, well, it's usually what the operating system kind of interfaces with in terms of the memory abstraction. But it only reads to a certain speed, and it only reports a certain amount. So you have, the other thing people used to do is put in faster memory. So you got an old computer and you want to make it run faster, so you buy bigger and better memory. Now, if it works, you're lucky. If it does work, because most of the time it's not going to work, you're only getting what the memory management unit is able to recognize. So if you got 3200 speed and you put in 12,000 speed, it's going to come back and say 3200 speed. So it doesn't really matter. So then if you don't put in what's supposed to be there, usually it doesn't work. Which is why you go to the store and you buy memory for an old computer. You end up paying more for it because it's old, because you have to buy slower memory that's older in technology that costs more. Costs twice as much as brand new memory. Or 3 times as much. So anyway, computer industry is kind of ironic when you think about certain things. Memory is one of those things. It doesn't help you. So, although nowadays we just buy what I call BIC lighter computers. I'm just familiar with, well, in the United States we had this thing called a BIC lighter that came out, like in the 1970s. Lighter, for fireplace, for smokers, for anything, just fire. So we had BIC lighters. Well, they're throwaway lighters. They were cheap because you used them till it ran out of gas and then you throw it away, or butane or whatever's in it, and then you throw them away. So that's how our computers are now. They're all closed up. You buy it, you use it, you throw it away. You buy a new one, you use it, you throw it away, or you sell it. So people were modifying the BIC lighters so you could refill them, and then they were selling them. There's a piece of plastic. It's cheap. It's not expensive. So you just throw them away. So now they make refillable lighters. I'm thinking, who in the world? You guys use lighters, by the way? I never quite understood the refillable one, unless you're like a dedicated smoker or something. And because I just have them because I have a fireplace in my house, and I actually recently we just started using it again. So I had to go out and buy some lighters. I'm like, oh, they still sell BIC lighters, which is why I remember this. But long story short, we lose them. You stick it on the table, it gets thrown away. Why buy an expensive? So the same thing with computers. Why buy an expensive computer when you're just going to throw it away? Because in a couple more years, or 1 year, 2 years from now, it's going to be upgraded to something else. It's going to be better. And you're going to spend a lot of money to upgrade it. It's cheaper just to buy a new one. Anyway, long story short, the same thing's happening with operating systems. It used to be that you upgraded your operating system on the current hardware and you just kept upgrading. Mac is still doing it. Windows, I think with 8, we're going to see a revolution going on with throwaway BIC lighter computers, essentially. You buy the tablet, you use it, you throw it away. You buy another tablet, you use it, you throw it away. Or I shouldn't say throw away. You sell it on eBay, or you sell it on Craigslist. Although some of them are pretty cheap in quality, so you could just throw it away. Like some of those Acers from the past. They're making better Acers now, but some of them didn't make it past one trip. So I bought one of those little netbooks when they first came out. Took it, didn't even make it to my destination with it because it broke in airport security. It just dropped. And I'm talking about less than a foot. I'm talking about maybe that much. It dropped, and the thing wouldn't turn on. I'm thinking, oh, I took it back to the store. I think I bought it. I don't even remember where I bought it, but they gave me a full refund on it. I bought it for this trip. I'm like, oh, a small little computer. This would be nice, And it breaks before I even get on the plane. But that's a BIC lighter computer. And I bought it. It was like $200. It was a BIC lighter computer. But you get what you pay for, I guess. Anyway, slight tangent, but execution of the user mode and the kernel mode. Some textbooks call this a dual mode operating system. I don't know. It's really just, it's switching back and forth. Only the user works in the user mode. Only the kernel works in the kernel mode. The user requests the kernel to do something, the kernel does it. There's no dual moding. There's no user switching to kernel and kernel switching back. But a lot of textbooks actually present it like that, like a switching system. it's no switching back and forth between your world. You're never in kernel mode. You never get to touch it because that was the original creation. That was the original design behind the system. It was called a protective mode. You lock it down. You don't touch it. So you don't let the user touch it. So how are you going to switch to this dual mode operating system? But you often hear it called dual mode. So you got the several data structures. These guys are needed to implement kernel services. 3 structures, a process table. This is what I've been calling the process control block. Process table. Contains an entry for every process in the system. You got your open file tables. That's a good one. Contains a list of every open file in the system, and it's usually organized by user. So you have open files by user. Also, the word file is kind of an interesting word. Everything on a Unix system is a file. If you haven't figured that out yet, sometimes you go through the exercises and you go, why are they calling this a file? Why are they calling that? Drivers are files, files are files, directories are sort of like files. Everything's all the same thing, which is kind of the weirdest thing. When we talk about file systems and inode tables and everything, everything's an inode entry. Even your device drivers, even your output, your terminal output is a file. So you can write from cat from here, cat out the output. All the commands that work on files work on drivers, work on everything, depending upon what it is. I shouldn't say it's not a universal concept, but the terminology is universal. So, let's see. So the execution of the kernel mode and the user mode when a process executes a system call, the execution mode of the process changes from the user mode to the kernel mode. All right, that's where the people come up with this dual mode kind of theory. It's actually true. Just don't think that the user has any control. You don't. It's the process that does. Which is actually kind of interesting because people go, well, what's the difference between a process and a thread? Actually, you guys know the difference between a process and a thread? That's a good question to ask. What's the difference between a process and a thread?
Process executes different tasks, whereas thread executes only one task.
Nope.
Thread is a part of process.
You're talking about mapping between threads and processes.
Thread is a part of process.
Nope. Actually, yes. Yes. Yeah, it is.
Lightweight process.
Huh?
Lightweight process.
Huh?
It's nothing but a lightweight process.
No, no. Okay. So, from the traditional people that describe this, from originally, you're both actually right, but except for you. You guys are on the right track. A process is a user mode thread. So a process is the terminology used in user mode, and it represents the running program. So if you want to remember it, P for program, P for process. Kernel doesn't know anything about processes. It's the kernel's abstraction takes a thread, gives it to the user as a process. The thread is mapped, the process is mapped to kernel threads. So the thread is down here. So the thread and the process are two separate things. That's why I say a thread is not a process. A thread is not a lightweight process, but you take systems programming and they tell you, oh, a thread is a lightweight process. It's all a bunch of textbooks and a bunch of textbooks. But in reality, the thread represents the process, but the thread lives in the kernel mode. The process lives in the user mode. In the old days, they had one-to-one, one-to-many, many-to-many mapping, where you had a ton, this is going to your answer, ton of processes mapped to a ton of threads down here. Or you have, what did you say? Threads inside of a process?
Thread is a part of process.
Yeah, so technically you're right too, because these threads are representing this process up here. So you could have two threads. So if you have one process up here, you could have two threads down here. Right now, Windows, Unix, Linux, everybody goes one-to-one. One process down here, one thread down here, one process up here. And that's called the thread to process mapping. So they call it mapping. The reason why they were trying so hard to make it multi-threaded for the processing, multi-threaded process programs, was because they think, oh, better execution time, right? Because you have multiple entries in the PCB, process control block. So you put 12 threads in there for that one process out there, and it gets twice as much CPU time. Well, it's a numbers game. And then they figured, and then it was confusing. how do you know which one of these threads is mapped to which one of those processes? And then we had multiple processes. And there's a UNIX v something system that has multiple processes up here mapped to multiple threads down here. And they're intermixed among all the processes. Like this process A, B, and C. Process C is mapped to process A's threads. So they mixed and matched the mapping to make better efficiency because why load it in twice? And then they switched everything around and went, wait a minute, we're all wrong about this. This is really the wrong way of doing it. What are we trying to do? We're trying to avoid work. We're trying to avoid having to load something up. So now we're going to have this entry work with all of these processes up here. You know, let's do it differently. Go back to one-to-one and put up shared objects. Put it up here. So if you have a program that's going to be shared, a library that's going to be shared among multiple processes, instead of mapping it down here, just stick this up here and have all these guys linked to it. And then we got shared objects.
And that's how they made it synchronized. Like
and that's how they synchronized it.
Thread is complete, it will release to the open mode.
Yep.
And one more process comes in.
Yep. So yeah. So a lot of people think from a systems programming perspective, they go, you know, the teacher says, oh, make a child thread and make a parent thread and a child thread and do all this other stuff. And so then students think, because they're using pthread library, that they're working with a process. But that's a system call to tell, which is actually kind of interesting. It's a pthread or POSIX threads system call interface library to tell the kernel to make a thread. And the thread lives inside of your process that you made. So the child thread gets a copy of the parent's process space, and then it gets its own execution space. So it gets its own stack. So the child has its own stack so that it can use it to do it needs to do something because it doesn't want to corrupt the parent space. So then we have the control that goes between the parent and the child, and then the release from an interrupt that happens when the when the child goes away and signals back to the parent, okay, child's gone. Then we have all of the thread processing stuff. And then if we're going to do it this way, we're going to load up multiple shared objects. And we're going to have threads down here that are singly mapped to processes up here. Then we go into IPC libraries for inter-process communications. We come up with this concept of the semaphore. We got the signal interface. So we can send signals back and forth. Because if we have the one-to-one mapping, one thread down here with one process up here, we got full control. We know exactly which one this belongs to, and one belongs to one. Easy mapping. So we can say, okay, you know what, you talk to you, and the kernel can be the traffic guard and control all the signals between the processes and all the inter-process communication that goes on, and support the libraries for it. The only reason why we could do this in Unix and you can't do this in Windows is because there's no system call interface in the user mode in Windows. It's completely blocked off. So we can't work at the thread level. You can't create threads on Windows because it's not available. It's just not given to you. So we know the difference between threads and processes? Okay. I mean, you're right, because all the textbooks in the back who answered to the thread process are lightweight. If you read, go to the bookstore, go online and Google it, or read in the textbooks, they always say, thread is a lightweight process. And then it's undergrad students. They go up and they go, yeah, thread's a lightweight process. And they always say that to me, and I'm like, no, it's not. It's not. What's lightweight about it? And then they usually can't answer a question. I don't know what's lightweight about it. But that's what they tell you. It's like a easier way of abstracting it because they don't expect you to know anything about kernels or processing or process control blocks or mapping. If you have to do that, then you have to explain mapping to them. You're hanging to mapping. Okay, thread's a lightweight process. Okay. Multiple threads all live inside of one process. They do, actually. They all get a copy of the parent. They do, theoretically. But they also have their own processing space. How else are they going to process? They're going to corrupt the parent. So, anyway, usually if you go into an operating systems design course, then you get all this stuff about how to create your thread models, how to do your thread mapping, stuff like that. All right, so I think I killed the thread stuff here. User mode, kernel mode, process, so process table. So here's a flow of control during a system call as an example. The user process invokes a system call, for example, open. Open is pretty generic, actually. Actually, the funny thing is if you look at some of the driver calls, open, close, read, write, pretty generic wording. So every driver's got a write, a read. If it's a device that, like an I/O device, it's got to read and write to a pipe, which is some, abstraction of some sort. So they open. So every system call is allocated a code number, as I was mentioning before. So open is a code. So you can call everything open. And it just goes down to different codes. But how's the user going to know what 95473 is or something? You don't know that. So then we got a C routine library version of the system call. Places a system call parameter and the system call code number into a machine register, and then executes a trap machine instruction. Switches to kernel mode and kernel code and kernel mode. We all know what a trap is? Well, here's your definition. Let's see if this definition makes sense. A flow of control, so a trap instruction, there's no definition here, it uses the system call number as an index into the system call vector table located in kernel memory. Alright, so what do the operating systems and the Unix textbooks of the undergraduate classes, what do they tell you a trap is? I'm sure you guys heard this one. It's just like the lightweight process. Lightweight. It's the same saying practically. You guys remember what traps are? Assuming, because you guys are grad students, so assuming you've had some exposure with this. A trap is a software level interrupt. It's a software interrupt. What does that tell you? Same thing as a process. Thread is a lightweight process. You can't make your own interrupts. They call it a trap because it wasn't generated by the hardware, it was generated by the user mode. So it's a user mode instruction that generates an interrupt. You're thinking, well, no, only hardware can generate an interrupt, seriously. Which is true, but if you're looking at an interrupt table, it's telling the kernel to go to the table. So it's not really a software level interrupt. There's no such thing as a software interrupt. You only have hardware interrupts. There's no such thing as a software. But the textbooks always tell you, a trap is a software level interrupt. So it's just like the thread is a lightweight process. It's the same kind of misconception, but it's easier to understand it that way. It's generated from software instead of hardware. Didn't come from the computer system. It came from something else. So the user mode and the kernel mode can generate traps. The kernel mode generates traps all the time. The trap is the interrupt that's sent that says a running process needs to stop, go back to the process control block, update it, start another process. So CPU schedulers use traps or interrupts, interrupt-based schedule. But then the textbooks, they say, oh, it's an interrupt. It is an interrupt, but the CPU isn't. The CPU could actually be on a timer to generate an interrupt that says after so many clicks, interrupt. Interrupt's a signal, gets sent over to the, turns into a signal, it gets sent over to the kernel and says, okay, stop this running process. Update the record system we have for it and start another one. So we have multiple processes running simultaneously, but it's running fast enough, switching back and forth fast enough that we don't know that it's not running simultaneously, theoretically. But anyway, so the trap is instructions. So it uses a system called number as an index from the system called vector table. An array of pointers for system calls that code is associated with instructions that the kernel is supposed to do. And the code corresponding to system call executes kernel mode, modifying the kernel data structures if necessary. So it's all about the kernel understanding what the instruction is and then using that instruction to, hello, I heard you coming down the hallway. So now you guys know to wear rubber-soled shoes. That way everyone in the class won't be listening to you as you're walking down the hallway. It's actually nice because then you can hear the attendance person. If she's wearing hard leather soles. So. Alright, performs a special return instruction that flips the machine back into user mode. Oh, I hate that. It doesn't flip the machine back. There's no flipping going on. There's no switching going on. Returns back to the process's code. I got this from an old systems programming book. So they give you the slide sets that go along with the books. So I actually have to disagree with some of the things. Like there's no switching that goes on between the two modes. It doesn't like one turn off and the other one turn on. They both run simultaneously. So it's the control and the process execution. Yeah, that abstraction. So now we got our synchronous versus our asynchronous processing. So usually processes performing systems calls can't be preempted. Yeah, you're not going to interrupt a call that's opening up a drive, that's writing a file, that is doing something because you're going to have corrupted memory. You're going to have corrupted process. It's not going to work correctly. So the process must relinquish voluntarily to the CPU for the CPU example for waiting I/O to complete. Alright, so let's go back to the process control block in Unix, Linux, see how things work here. We have a scheduler that is now multiple queued. So we have items that are queued up because not everything can run at one time. Kernel can only run one operation at a time. So then we have a queuing system, multi-level, which is the current day system. It used to be one queue with priorities. Now we got multiple level queues. One queue has I/O in it. The other queue has CPU-bound processes. Another queue's got flipping back and forth. And then the textbooks, going back to the operating systems textbooks, they always say, it's a short-term, a medium-term, and a long-term queue. And what's the difference between the short-term, the medium-term, and the long-term queue? Well, processes, they spend a shorter time in the short queue. Longer time, long. Oh, it's as bad as some of the other stuff. It's not short, medium, and long. Scratch that. It's CPU bound, I/O bound, and we're confused about what to do. That's the third queue. Medium. We're confused. We don't know what we want. We're just sitting in the medium. We're waiting to go one way or the other. So why do you want to do it? Because technically, okay, let's go back to why they call short, medium, and long. Technically, the short-term queue is the CPU-bound processes. Why? Because they're going to stay in the queue a shorter amount of time because they're only going to get CPU bursts and then they're going to get out of the queue. Where are they going to go? Probably the long-term queue, where they're going to stay in the system longer. All processes come in through the short-term queue. And then people go, oh, well, shouldn't that be called the job queue? So then some textbooks call it the job queue. So you get the queue that starts out the beginning of every process's life. It has to get CPU time. Otherwise, what's it going to do? You can't run a process without CPU time. So the process ends up in the short term or the long, or the job queue, depending upon how you want to call it. It gets a couple of bursts or so, whatever it needs, to figure out what it's doing. If it's confused, it goes into the medium. If it knows it's I/O, it goes directly to the long-term queue, which is the I/O-bound processes. So, multiple queue system instead of one. So then you can separate out the PCBs. We have a process control block for the short term, the medium term, and the long term. If you want to do it that way, you can do it one block for background, one block for foreground, one block per user, one block per process, for CPU. Because if you put another CPU into the mix, then you got twice as much complexity, because then you got to figure out, well, how are we going to use them together? So that's the interesting thing. Is if you're a CPU scheduler and now they gave you another CPU, it's kind of like working in a factory and all of a sudden they give you a bunch more workers. Oh, what do I do with these guys? Well, you can throw them in the current mix, or you can put them on special projects. So a lot of your mobile devices, they're on special projects. If you have a Droid with 2 processors on it, one of them's just doing the telephone services. It's a smaller one. It's just going to do incoming calls, outgoing calls. It's running the kernel. It's running everything that is bogged down by that underlying operating system. It's all running on one core. And then the other one is all your apps. So if you got that, you're going to get the whole bionic thing. You're going to get the whole, like, wow, it runs faster. Yeah, you have an entire dedicated CPU to all of your apps. It's going to run much faster than if you have to share it with all the kernel stuff that's going on underneath it. Talking about that because Android's a dialect of Unix. Linux, it's Android, it's not, it's totally different, but it's underlying, there's a kernel, and it's an underlying Unix platform that's been modified. So it's not 100% Unix, not even close, but it's a Unix-based system in concept. So they take this processor, CPU scheduler over here, CPU scheduler over here, switch it out. Now you got dedicated process, you got the best of both worlds. So, all right, so going back to the I/O thing, synchronous versus unsynchronous, the long-term queue is going to be non-preemptive. So your jobs are going to start, there's a seat in the back over there. How did we end up with a full house today? What did you say? Oh, he's there? Oh, I'm sorry. I thought it was somebody's computer. Did we seriously run out of seats? Hold on.
I'll go grab one.
Are you sure?
Yeah.
It's bring your own, I have a chair over here. It's bring your own chair day that I do. Alright, so I was talking about long-term and short-term. So your long-term or your I/O queue is going to run slower because you're not going to preempt those processes. The call to go open up the CD-ROM drive is going to start and it's going to finish before the next call is actually created or run. Your short-term is definitely preempted. So you have a little bit of CPU time for you, a little bit for you, a little bit for you, and we're going to go back round robin. Back to you, back to you, back to you. And we're just going to cycle through until we get it all done. So then we're going to share time. So here's how it works. Then we got the CPU being allocated to the short term and flipping to the long term. And then from the long term back to the short term back to the long term. That's why a dual CPU system is actually more effective for a desktop environment, because then you can put one on the long term and one on the short term. And then you got kind of like most of the modern day Android systems. So it's a little bit easier. Okay, so processing must relinquish voluntarily. Yes, the kernel sends a process to sleep and wake while the I/O is being completed. So let's go back to signals and inter-process communication. So the kernel has an entire library set of modules that are created for it to communicate with the threads. And it opened it up, let the user use the same libraries. So you can do a signal, you can create a semaphore, do mutexes, you can play around with the entire life cycle of the process. You know, we're going from all the different states. If you go back to your undergraduate operating systems book or Unix book, it says ready or new, ready, running, sleeping, waiting, you know, all those little process states it goes into. Well, you can do the same thing. Well, you don't have as much control, but you have a little bit of control over it through the system call interface. So when you take a systems programming class, they have you write thread programs that, you know, here, capture this signal, or, you know, do this, do that, create a semaphore, do that. How's your practice with the interface? You don't have to do it for this class. It's more of a systems programming course. Scheduler does not allocate sleep processing anytime. No, not at all. So if you put a user mode process to sleep, it's not wasting any time for the kernel, because that thread that's down there in the kernel, it's marked sleeping. So it's a great way to kind of pause some execution. The other thing I forgot to say was between the foreground and the background mode of the user mode. So user mode's got foreground and background automatically by default. Any system does. Use the ampersand, you put it in the background. Your process scheduling, you have two different schedulers for foreground versus background. So the foreground is going to get a higher priority. It's going to get run faster. Background is going to be delayed. All the foreground stuff is done, then we do the background stuff. So it's kind of secondary. Why is that? Because it's not taking up current time for the user. It's a background update, or it's a backup, or so part of the admin's job is to kind of figure out what can be run in the background so we can get everything done without interrupting the user experience. Interrupts and exceptions. So we got the system call device and the I/O peripherals and the clock to interrupt CPU asynchronously. So we have devices such as the I/O peripherals and the clock, they constantly asynchronously send out information. So we have synchronous activities versus asynchronous activities. The kernel runs asynchronously. It doesn't do things in real time, which is kind of the most ironic thing, because you'd think it was it's not in real time, it's asynchronous. Real time is synchronous processing, which happens when it happens. So if an interrupt from the hardware gets sent to the operating system kernel, and you're running in an asynchronous mode, then you go, oh, here, put it over there, put it over there, put it over there. I'll get to it eventually. So the kernel queues all of the interrupts and everything like that, and then works on it when it needs to work on it. It's got to save it, because otherwise you're going to miss it. So it captures it, saves it, catches it, saves it, puts it aside, and waits till it's ready. So we got an asynchronous communication. So on the receipt of the interrupt, the kernel saves its current context, which is what it's currently doing, frozen image of what the process was doing, and determines the cause of the interrupt and the service of and services the interrupt. It's not always an immediate, we're going to stop, because we have to say what we're doing. So if we're running a process, we have to update the process control block. Then we got to go to the interrupt table and say, okay, what do you got going on here? It's going to get a higher priority. It's going to interrupt. It will definitely interrupt running processes, which is why you have something wrong with your hardware, your whole system doesn't work right, because the kernel is going to be servicing those hardware errors, and then your processing isn't going to work, or not as fast as you'd like it to. Devices are allocated an interrupt priority based on its relative importance. Hard drive's pretty high in the system. Main memory is the highest. If you don't have main memory, if your physical RAM is bad, your system's not going to run. So whatever's going to take the system down the soonest is essentially what's going to happen, is going to be the higher priority base. So memory, all categories of memory usually come first. So main memory, or that physical RAM is first. Hard drive second. Why? Because a hard drive is generally storing the inodes. So it's generally keeping track of or keeping a backup copy of the file system. You can't commit your file system because you have a file system error. It's still going to work. It's not highest priority. Oh, are we going to take attendance? Oh, no, it's okay. Let's take a break, because some of these guys have been here since the beginning. We just pause. Alright, so I'm going to continue where I left off here. Interrupts and exceptions. So we're talking about how the kernel runs in an asynchronous mode, and then everything else runs synchronously, which is actually kind of interesting. Even the user mode sort of runs synchronously. Everything happens like in real time, or as it goes, it doesn't. We don't work and stop and work and stop and work, and we want things to happen now when things happen. So anyway, long story short, the processing of an interrupt, once it's received, kernel is going to save its current state of whatever it is working on, and usually referred to as the context of its processing. Save the context, service the interrupt, and then go back to whatever it was doing. So devices are allocated interrupt priority base. So we have different priorities on processes, different priorities on interrupts, different priorities on a lot of the different things, so we can keep track of importance. And importance has to do with the criticality of what's gonna make the system fail fastest. Memory is generally the first thing that's gonna have a problem. Hard drive is kind of secondary because of the file system, and then we have other things about the system that come kind of descending order, go down in lower priority. So when the kernel does service an interrupt, it blocks out lower priority interrupts, but services higher priority ones first. So if you get more than one, the highest priority is going to end up happening first. So here's our typical interrupt levels. So sometimes we have to prevent the occurrence of interrupts during this critical activities to avoid corruption of data. So the ones that are the most are the machine errors, the memory errors, as I was mentioning before, the hardware, kind of machine-looking errors. Clock errors could be a problem. So higher priority disks, network drives, higher priority processes, that is, network drives, terminal, software interrupts are very low priority. So the high priority ones are going to be machine or clock oriented. So lower priority ones are going to be software interrupts. That's something that the kernel would actually do in terms of something the kernel is going to send down. So the interrupts are serviced by kernel interrupt handlers, and you can make one in the user mode actually to do your own interrupt handling. But you have to really pretty much create a demonstration or an abstraction of it because you're at the kernel, you're at the user mode instead of the kernel level. So the kernel actually has to handle things fast because it doesn't want to lose any of the other ones that are coming through because this is an asynchronous environment and it's working asynchronously instead of being synchronous. Kernel interrupts are coming in through synchronously, or all at one time, I should say. So it keeps track of it in a data structure so they can basically put it in some order, some plan, so that it can service all these interrupts. So an interrupt of higher priority occurs while a lower one is nested. Nesting will occur. The higher one will get serviced first. So it doesn't really matter the order that something shows up in. It's on a constant evaluation to see, is a higher one coming in? Is a higher one coming in? Let's service that one first. Kind of priority. Alright, so then we have disk architectures. So the disk itself and the file storage is an abstraction of the kernel. So a lot of people think, oh, it has something to do with the disk. Well, actually, beginner MIS people actually think it's something to do with the disk. No, you know, it's probably nothing to do with the disk. In fact, the storage on the disk has nothing to do with anything except for the file system that's being used. So the file system is determining the disk architecture for the most part. Bad file system, bad storage on the disk, or unreadable disk. So the disk is split out in a couple of different ways. Traditionally, if we're looking at hard drives of the old magnetic plate variety, not the solid state, but the old traditional style, we have a bunch of plates. And we have a bunch of arms that go cross and forth on these plates, and a couple of different levels. And yeah, there's many different abstractions you can do for this. So operating systems and Unix in the past was designed so that the file seek, file write, file read minimizes the hardware, minimizes the use of the ARM. So if you have a system, so the kernel has to go find the stuff. When there's a request to get something from a hard drive, the kernel has a data structure that it's going to use to go find it. So it's going to have it be a disk scheduling algorithm that goes out and finds all the blocks that are associated with a file, or all of the information. So the goal of the design of this algorithm is to minimize the ARM movement. Because if you have moving parts, they generally wear out first. Actually, most of you probably have moving ARMs on your computers. Even the older MacBook has a moving old style disk. So you shake the thing too much, shake the ARM loose. You don't, you have solid state drive. I have solid state. The newer MacBooks have solid state drive. Solid state drive, totally different, no moving ARM. So they got rid of the problem. So now you have, well, if you're looking at a solid state drive from an operating system from a Mac, you'll have a brand new, if you can control the hardware, you can control the OS in terms of the algorithm used to seek that drive. So now we have a brand new disk scheduler in Mountain Lion, actually, or Lion. I can't remember when it started. Not in Leopards, not in the Snow Leopards or the Leopards. It started in the Lion, and then now it's in Maverick as well, where it has a totally different philosophy in terms of reading from that disk. And it minimizes the read and it does caching instead, which is actually kind of interesting. But the boot's faster because the boot sector is running at a faster speed. And the whole thing can be optimized. So if the operating system can take advantage of the hardware, which is the point I'm trying to make, you got a better system. They're both supposed to work together and complement each other. But if you have a generic system where you don't know if you're going to have a moving ARM or if you're going to have a solid state drive, you're going to be a little bit slower until everybody's off the moving ARMs to update that disk scheduler. So what do you do? In the operating systems course, you learn about all the disk scheduling algorithms. You have the elevator one, which is actually pretty popular. It creates even motion. So the ARM, it's like an elevator. ARM starts at one floor, goes to the highest floor, services all the requests. On the highest floor, comes back down to the low floor. One sweeping motion back and forth. Because what you don't want to do is jerk it around all the way. Up to the 5th floor, down to the 2nd floor, up to the 9th floor, down to the 5th floor. Because then you're going to wear out the hard drive. Because you're going to wear out the mechanical mechanism. Your kernel is responsible for this. Because your kernel is designing or using the module that reads from the disk. So it's interfaced with the hardware. So it's always the kernel's responsibility. So if you think about slices of pizza called sectors, and this is kind of rudimentary information, you get this subdivided into eccentric rings or tracks, and you have the blocks and the individual areas where you're going to keep track of stuff. And you got block sizes here, the whole 4K bytes. It's going to be dependent upon the system, dependent upon the algorithm used for this, for your disk architecture. Disk architectures are going to change depending upon the media that you're talking about, solid state or the old ARM style ones. Several different variations. Many disks contain several platters in the old days, so we had levels to go up and down, stacked up and down cylinders. Big issue, sequential blocks are much faster than random blocks. Problem is sequential storage, not very efficient. So now we have this concept of a file system. It's a totally made up concept from operating systems, which is actually kind of interesting because it does mimic the Windows folders when they came out, because we had directories and then Windows turned them into folders. It does mimic the file cabinet. Where you have files inside of it. But the whole this concept came along long before that. You take a bunch of blocks and you group them together and you call them all belonging together and you put a name on it. So if you're going to use that philosophy of the file and that terminology, that's how everything on the system turns into a file. Device drivers are files. Directories are files. Files are files. Everything's a file. Character files, block files, binary files. We have different types of files. But if everything's a file, what is it? It's just storage. So by concept, we get a bunch of blocks and we associate it with something. Because we put something on the disk, labeling it something. One's a device driver, it's a file. The other one's something else, it's a file. And you're reading right to the files. What do you mean? You're going to the memory address, you're picking up what's there, you're using it for something. And you're gathering the whole bits and bytes that go together for whatever it is you're using. And you're going back and forth. So the terminology is actually kind of interesting when you compare it. So a sequence of contiguous bits to read is kind of impossible. There's a latency delay between each block that's read. Communication is between the disk controller and the device driver and all the workings with it. So the idea then is to conserve. It's not on the slide. I'm going to talk over the slide because I want to cover something that's not in the slides right now. The idea in terms of using a file system concept is to be able to cache it off the disk. So going back to what I was saying before, if you look at the kind of hierarchy of memory and the hierarchy of how things are closer, when you talk about memory, going back to what I said before, the closer the CPU, the faster. So you want to bring it closer because it's faster processing. So everything that's on the hard drive gets accessed fewer number of times and it gets used the most. Everybody puts everything on the hard drive. So you have a huge caching system where you take from the hard drive, and sometimes the cache is actually loaded on the drive. So hard drives with more cache have faster access speeds. Because instead of putting it back, you just bring it forward and assemble it on the cache and then bring it all together. So there's read, write through the cache, makes it more efficient. But long story short, we want to get it off the hard drive and store it locally. So we stick it up into memory. So then we have buffered I/O, or buffered processing of files. If we're going to do that, we'll do it with everything. Device drivers, everything's buffered. So you can load it up into memory. Well, you do the same thing with kernel modules. You load them up into memory. So it's really all the kind of the same concept, but it's extended towards all of the other utilities and the features that go on with that operating system. So going back to this disk architecture, we want the consecutive data to be on the same track. We don't want to go in between different layers. We want it all on the same track, same location. We don't want consecutive blocks that are three sectors apart. You know, we want to group things together. This is the old-fashioned way of doing it. Extend file system support with large consecutive chunks at once. Needed for data-intensive application. That was always done in terms of blocks. So when you think about the storage done today, it doesn't really matter actually how it's stored. So there has been a lot of history in terms of, you know, all the techniques to minimize the wear and tear on the drive. Plus also the more you move the ARM, the more heat you generate. The more heat you generate, the more fans you got to put on the sucker. So it's another, you know, makes it, and then I don't know where you're going to put the fan. makes the system bigger. So, long story short, it causes a lot of issues associated with the architecture. Change the architecture around. We don't really necessarily need to worry about this same kind of concerns anymore. So it's operating systems in general. You'd think Unix, but no. I don't think there's a Unix build that works with solid-state drives right now. The idea now in most modern-day systems is take a bunch of drives, put them all in there, and then overlap the file system among all of the drives. So you have spanning disk images. And then you're working with a disk image. So most of your Unix systems are disk images anyway, which is great. Because it's not attached, it's using the media, it's using the hard disk, but it's not necessarily attached to it. It doesn't have to read and write from it. It's kind of like what we're doing in memory. So a long time ago when we explored with reading, writing, buffering, all this other stuff, then we came up with, well, we have buffered I.O. and non-buffered I.O. We have all these other kind of concepts that came out of it to make it more efficient. Now the biggest trend is, let's just not worry about it, we'll just create a disk image. And the disk image can just work anywhere and just do anything. Hard drive breaks, take it out, put another one in, put the disk image back on it. So it's a little bit easier now. What's this disk image have in it? It has the file system. What's the file system? It depends on what system you're on. It could be inodes. It could be a tree. It could be a linked structure, like a linked list structure. So this is where data structures kind of helps you in building file systems, because file systems are all about data structures. So the linked list, is it a tree structure? Is it a table structure? So the primitive one is the FAT file allocation table. So we've got FAT12, FAT32, FAT 16, all these different versions of FAT. And they go on with FAT. Depends on the shape and style of the table. So take a table, stick everything on the disk into the table. So we've got file A, file B, file C, file D. File A is block this. File B is block that. Stick it all on the table and stick the FAT table under the drive. System boots up, go to the FAT table, read the FAT table. Now you know what's on the drive. Simple, easy to work with. What happens if the FAT table gets corrupted? Done. You're done with the drive. Where's the FAT table? Right in the beginning. What gets used the most? The beginning of the drive. Just think about all the different arm movements. It's the beginning and the end of the drive where all of the physical wear and tear happens. Just like in any device from a physics point of view on the market. It's the, if you get something that stops, that's where the FAT table always gets corrupted. So will the end of the drive. You fill the drive out, the more stuff you stick on the drive, the more likelihood that you're going to lose it. So you don't want to fill up the drive because the end is going to get destroyed. What's at the front? The FAT table. So you build utilities to fix the FAT table. Why? Because the arm's going to bounce back or something's going to happen from a mechanical perspective. It's going to wear and tear on that end of it. You're going to have a problem with it. You have to rebuild it because it's all about mechanics. So long story short, weakness, but also benefit. Most of your little thumb drives are still using FAT. Why is that? Well, because is the operating system going to know about what's on your disk? No, but you can take your disk and just put it into any computer that you want, and it recognizes it, reads the FAT table from the disk, and says, here's what's on the disk. So FAT's very good for that, good for portable, removable media. So, it's good in terms of reliability. But more efficiently is to be able to treat it as part of the base system. So Linux has this thing called inodes, or Unix uses inodes. It's a tree. So you build a tree structure of all the data that's on the disk. You put it in an inode. And where's the inode? It's going to be stored on the disk. But, on the boot disk actually. But you can move it around, you can be a little bit more protective with it. It's not always in the same spot. You want to write a virus for a Windows system? Pretty easy. You know where the FAT table is. You know where the boot sector is for that matter. You know everything. So you might as well just throw security out the window with that. FAT's not very secure. Inode's a little bit more secure, but here's the thing. So you build a huge tree, you got multiple computers that all work together, they're all connected in the same tree. When I say computers, I mean workstations. I mean Unix box over here, Unix box over there, one in Colorado, all connected together in the same inode tree. You stick your USB disk in there and it's fat. Well, no problem. You can mount it into the tree structure so it shows up in your user home directory, and it has an entry. Everything has an entry into the inode tree. If you have that, then you can make a directory structure that spans multiple drives, multiple systems, multiple networks. And you have, it's kind of like the internet, if you think about it. And you can get to everything everywhere. And then now you have truly distributed file system going on there, because it's distributed over multiple computers, all the same file system. So you're logging into an Amazon server. And this Amazon server, half of your accounts probably aren't on the same physical device. Some of your accounts are probably on a server out here, some of them on a server over there. It actually even might move around, depending upon who's maintaining the file structure. But you all have the same abstraction of being in a home directory and you've got your account. It doesn't really matter where your account is, though, in terms, because you're in an inode structure. So you could log stuff into it. You can actually mount. You can actually use the mount command and mount your USB disk into your Unix file system and read and write to that if you wanted to through the file system. Through the inodes. So if you take a look at the concept of building a better file system, and you're looking at a fat table from a data structures and algorithms perspective, it's a table. What's a table got? Entries in it. So you got to worry about, okay, you're going to read everything in there? Yeah, pretty much so. You're going to read the whole thing to find what you're looking for. Or you can, we could probably make a better algorithm to traverse that table. It's still better than another non-structured file, non-data structure. So then they went, well, okay, let's just put an index on it. So then you got indexed file systems. And you're looking at some of the NTFS. You're looking at some of the HFS Plus. You're looking at some of the other ones. Well, HFS Plus uses a journal. Windows uses an index. So you got, okay, what does that mean? It's like, instead of going to the table, just load everything up. Just like databases, just load everything up, and then we'll go to the index. Instead of going through all that stuff, we find the entry we want. The index, it's a pointer index. You say, oh, it goes to this. Here are the memory addresses, there's little blocks and everything we need to find our file. Index is faster. So you look at the index and you go through and go, okay, this one. And we want that one. We want this one. The journal is an extension on that concept, and I'm totally simplifying all of this stuff, actually. So it's a little bit more complicated than I'm making it sound. But in essence, they're just different techniques to organize the data that's on this disk. This is what we're calling the file system. This is the algorithm that creates this abstraction. So the file system itself is an index or a journal. The journal, they did backups on the journal and they tracked the changes on the index. So journal's not bad because you could run utilities to fix the journal. Journaling is historical. It's an index with history and an index with extra features, but it is an index. So an index system is much faster than sorting through raw data. Inodes are even faster because now we're not using an index, we got a tree. If we just want home directory, we just go to home directory. We just got here, then we get the absolute relative, and then now you know like what makes that efficient. Doesn't matter what else is out there. All you got is what you're looking at. You don't have to go through anything. You got a starting point on your tree and you go down the branch. That's all you have access to. Then you're in good shape because the searching and the sorting, it doesn't have to go through anything. So you can dissect it out from a tree perspective, run an algorithm on it, and then much faster to traverse that tree because you cut off 90% of it. You only got 10% or 5% that you actually own and have access to. So most file subsystems provide support for regular files, directories or folders, special files. So special files that correspond to peripherals such as tapes, terminals, disk drives, inter-process communication mechanisms such as pipes and sockets. So everything on Unix is a file. So a pipe is a file, a socket's a file. It's all file abstraction. File abstractions are all associated with inodes for the most part. So there's your inode. So here we go. By definition, Contains permissions, owner, groups, and last modified time. So types of files, regular, directory, or special file. Your device drivers are special files. Directories are directories, files are regular files, files. But they're all files. So we're looking at a system that's going to hold all the information about all the files in your tree entry. It's calling it a tree. It is a tree format. It's not exactly like a traditional, like a binary tree or a red-black tree or a tree from a data structures perspective. It's a tree, though, in terms of the way it's constructed. But it's not a traditional tree from a data structures book. It's an inode list. So you can tell the differences with the file systems just by looking at a Windows as an example. You're going to use an index. You're going to change the file name. All of the information associated with the file is with the file. So if I loaded on a file in a Windows system and I called it helloworld.exe, and it was a compiled version of a C program that was for Hello World, and I take out the exe and I put in there BAZ, or I don't know, I just change it to something. Then the next time I go to run it, it's not going to work because all of the information is stored with the file. So unfortunately, you're hosed unless you change it back to exe. All the information about what day it was created, what day, you know, it was modified, yada yada, all stored with the physical blocks. Takes up more memory on the disk. Fewer files fit on the disk because you have all that other stuff in the files taking up more space. Files are bigger. Remove all the stuff from the disk because what we were trying to do way back in the beginning was conserve the disk space. I'm talking about the first hard drive that came out had 5 megabytes on it. You know, it's like twice the size of the floppy disk. 5 megabyte, 10 megabyte disk. How many files are we going to stick on there? Well, we're going to store everything on the disk associated with the files. Put it in a fat table and put the fat table on the disk. Not very efficient. So to make it, just pull it all off, put it in the inode list. Take the inode list, condense it down, and then build the inodes. So what you got is a bunch of data that gets formulated into the inode when it's read from the disk. So it's not, the whole structure's not there. The structure's built when you boot the system. Build the inodes, put stuff into it, makes the inodes dynamic. So you can mount, unmount. So we have mounting and unmounting in Unix to add things into the inode list. First thing we do is mount the file system. So if you look at some of the boot up scripts that are done from a kernel load perspective, last thing that happens is mount the file system, mount it at an entry point. So you have an entry point, and then you have the type of file system. Is it NTFS? Is it extended? You know, is it HFS plus? Unix supports everything. We just have to say, hey, this is a FAT disk. Mount it in as a FAT, or mount it in as NTFS. So you have the ability to mix and match different file system types. You're not stuck to just one file system. And you have the ability to adjust and change depending upon what server's up. So if you have 5 or 6 different database servers for a bank, and you have one that's faulty, you can just take it out, put another server in there. It has the same setup on it, mount it in. So it's not like it's on the server. So it builds an abstraction of taking the disk information, taking it off the server, putting it up into the inodes, and loading the inodes. The inodes are going to span all these servers. So it gives you more fault tolerance, more flexibility in terms of the systems, what's available, what's not available. So you have a mount directory. It's called database 1, and it's normally on that one. You just switch the inodes and go database 1. Oh, now you're on this one. Swap them around, change the file system mounting around, makes things more flexible. So it's better for distributed systems, long story short. So if it's a symbolic link, the value of the symbolic link is kept in the inode table. We think we did symbolic links, some symbolic files, symbolic directories. Show you symbolic links last time? Okay, good. Link. I think that was in one of the assignments, like maybe the last assignment.
Hard link.
Okay, good. Hard links and soft links. Yeah, that's what that's talking about. So you could take and create a link that's not really even there. That's a symbolic link. So, and why do you want to do that? Because all of the protection system is in the inodes. So let's say, for example, you have a directory and it's HR directory. And on the HR disk, you have everybody's salary information, everybody's personal data. You want to give the entire company everybody's data? Probably not. You make a symbolic link with restricted access. So you change the change mod access on the link so that it's read, write, whatever, to your subdirectory, or your section of the data. So you only have access to your information, and then you make that available through the website, or through the web interface. And then from a protective system perspective, you've guaranteed that this person is not going to look at anybody else's information. You can't. You don't have access to it. So for access, symbolic links are nice for access privileges, for creating a simpler abstraction for somebody. Like when you log in a company's server, you see your home directory. Actually, you have it. You have a symbolic link when you use clouds, or when you use Dropbox, or when you use all that stuff. You don't have access to the entire server. You have access to your account, your directory. So mostly through a symbolic link. So if it's a regular file directory, it contains a location of the disk blocks for the file or for the directory that you're looking at. So direct pointers to block 0 through 9. Indirect pointers to an entire block, which holds 10 to 10,033 blocks. Now that abstraction has kind of changed a little bit. Depends on the modern day system. This is antiquated beginning of time information. But inodes are pointers. And so you create a tree of pointers, and you're pointing to different locations. You just change the pointer address, and you change the entry in the file system. For FAT, you change it, it's done. It's permanent. There's no history. So then they indexed it. You changed it, you're done. Then they put a little temporary thing in there. I think you can still undelete, can't you? Can you undelete? In the old days, you used to be able to undelete. If you went up to File Manager, you see it's an index when you see File Manager and you see all the indexes by directory, file. They call them folders. Folders and files in the folders, and the folder's a subfolder of another folder. You go through the index and you kind of find where you want to be, and you delete something. Can you undelete it? I can't remember. You used to be able to undelete. On the journaled system, you have more information being stored, so it's more protective in terms of accidental errors and things. The biggest complaint in the old days was how inflexible FAT was, and then we also had file size limitations. We still have file size limitations. We can get a big, I just noticed this the other day too. I had a USB drive that was formatted for FAT. Or actually it was NTFS actually. I stuck a downloaded, it wasn't this class, it was my iOS class. I wanted to give, the upgrade, it was an operating system file. The file itself is a little bit over 5 gigs. And I have a 16 gig thumb drive. And it was formatted for FAT or for NTFS, I can't remember, it's probably FAT. It wouldn't take it. It says, oh, file system can't support the file size, too big. I went, too big? And then I realized, oh, this thing is 40. I bought it, took it out of the package, put it in, it was formatted for FAT. So then I went, oh, wait a minute now. Let's put HFS Plus on here. HFS Plus holds up to 8 or 8.5, 9 gigs or something like that for a file. Larger file support. So I'm like, oh, okay. Then I took the operating system, copied on, and worked just fine. The only problem is you take it over to a Windows machine, can't read it. Because your Windows system can't read anything or identify anything past a certain file limitation that's lower than the Mac system. So you can't have 5 or 6 gig files. Interesting, because now you take a look at some of the CDs. Have you ever took a DVD and stuck it into your drive and read it from a file system perspective? Say file 1, file 2, file 3, file 4. Actually, what you get is 1 gig files because the old FAT couldn't read more than a gig. So it's like 900 and something. Just under a gig, and it's split out. So you have 4 files for the movie. If it's a 2-hour movie, it's got 4 gigs on it normally. So then you got if you got 4 gigs, you got 4 files or 5 files, depending upon what you're looking at. So most of those DVDs have 5 files on it. Now they're making some of them with 1 file. Because we don't have to worry about that anymore, especially if we're not using FAT anymore. We're not using, so some of the format, the techniques for how people put stuff together and save information is highly geared towards the file system. So the biggest complaint in the past is you came from a Unix system and you had these huge files. And then the nesting is unlimited. No, I shouldn't say unlimited. It is much more deep on an inode system than it can ever be supported with on NTFS or on a FAT system. FAT's very limited. What I mean is the number of subdirectories nested inside of a main directory. The internet is Unix. That's the only way it's going to work. So then Microsoft has Microsoft servers out there. Limited because you cannot hold the same depth of directories. You cannot hold the same integration with other servers. It doesn't integrate with other servers, by the way. It's on an island of its own. So I don't even know why they do that. Obviously, I'm not a Microsoft fan, so I'm not going to say anything positive to begin with, but why did Microsoft get into the server business? They have no business in that area. The internet is Unix. It has to be Unix. It can't work any other way. Anyway, which is actually kind of funny because people don't connect to it with Unix anymore. All the clients are non-Unix, but the internet's Unix. Part of the problem is having to do with the file structure and the way that the system is going to create entries and how you're going to get your server in to mixing with everybody else. If it's not speaking the same language, it's not going to work. So usually standalone intranets, standalone closed off private networks. You'll find a lot of the Microsoft servers there with .NET on it just to support closed corporate systems, not public systems. So layouts of file systems. File systems have the following structure. What do we got here? Block. Well, some of this, again, kind of dated, but and there's a block, a boot block, boot sector, boot section, and generally it's still on the disk. You're wondering, well, what do you mean on the disk? Not technically on the disk. You know what you get from the manufacturer? It's the raw media. And then the file system puts the structure on the disk, which is why you can't normally take and format a disk with a different file system and keep your data. It's an all or nothing. You want to keep it in FAT and then use that forever? Or do you want to destroy everything that's on it and we'll reformat it for you for this system over here? So it's, you don't get a choice because you got to change. You have to, if you're going to use FAT, you're going to put a boot sector on the disk. The boot sector doesn't exist on the disk, which is actually kind of interesting because in the beginning of time, people went, I got a 3 gig hard drive. Actually, those were pretty popular at the beginning. In order to put a 3 gig hard drive on a FAT system, because we didn't have anything but FAT at the time, now we have 300 gigs with non-FAT. We have a higher system for Windows. They lost like 2 gigs of it, or 1 gig of it. They didn't lose 2 gigs of it. They lost like half a gig. They load it up and they go, whoa, what happened? All my memory's gone. I bought this 3 gig hard drive and I only get 2 gigs and a half or something on it. And I go, oh, it's the operating system. And part of it is the operating system, but the operating system is not only partitioning it differently, so it's got a backup partition, a hidden partition, but it's got a huge boot sector and a huge section for backup and a huge section. The operating system is just eating up your hard drive. So the concept in Unix, Linux, is the operating system doesn't touch your hard drive. It just takes what you got and uses it. So you got this, we'll just melt it in. You got that, you melt it in. You do what you want to do with the disk. So from an operating system's perspective, it's not trying to control your secondary storage. And then you don't want FAT? Take it out. Don't support it. Don't load it into the kernel. Leave out FAT completely. Then anyone who tries to connect with a FAT system is going to be sent away. You don't want, HFS plus, take that out. Just have extended. So your file system is going to be determining how big your files are, what's going to be accepted by the file system, by the kernel, what communication mode is going to go on, and then as the slide is pointing out, how the blocks are going to be formatted on the physical storage. So anyway, so secondary block, so first logical block's boot sector, and then we got our super block coming next. It contains the information about the free pages in the inode list. Not going to be first, going to be secondary. And then we have our inode list. It's a list that we're going to create the inodes from. So we're going to read the disk, take all that memory, create the structure, and then work from there. Never go back to the disk. We only go back to the disk when we need to write a change. No change, no disk. Terrible part. You shut the system off. You get a power loss and the system goes down. And then just how you have rebuild the you got rebuild the inode list. Fix the file system stuff. Well, 9 times out of 10 it's not going to work because you had temporary memory storing changes that were supposed to be committed to files on the disk, and the disks are gone. The disk is not present anymore. Long story short, it's impossible normally to recover 100% from that, but there's ways of fixing things. What ends up happening is if the inode list gets corrupted, the whole disk doesn't read. So pretty much you can fix the inode list, and then you lose a bunch of data. Is the data gone? Not really. It's probably on the disk somewhere, but good luck trying to find it. Not going to find it. So in terms of reliability and security, that's better. That's reading and writing constantly to the disk. Slower, but safer. You pull a fat disk out, no problem. You pull a disk out of an island system, problem. It's all stored in RAM until you commit the change, you unmount, you write the file system out. You lost all your work. You lost everything you did on it. So not very safe. More efficient, but not safe. So from a personal computer perspective, and you're going to make an operating system that's going to run on tablets and notebooks and stuff, you're not going to go with an elaborate inode thing because that's going to be too hard. How often do you shut a server off? Never. How often do you shut off a Windows system? Every single hour or a day? A couple of times a day, kind of probably. People don't suspend it. People don't do anything. They shut it off. So you're going to lose your data. Not as reliable. You're going to remember to write things out. Close the file system to unmount the disk. No. You're not. You're just going to pull it out. Which is fine. You can pull it out, no problem. You're not working with inodes. So, data blocks start at the end of inode list, yada yada. Conversion of the path name to an inode. So, if we got a tree, we're going to take the path name that we got, convert it to an inode symbol, go to the tree, look it up in the inode symbol, and then go back and convert it to a path name. Why? Because path names are for humans, and inodes are for the kernel. Just like the interrupts have a name, but the kernel doesn't know those names. The human knows the names, the sig, kill, and the this and that, all these other things, or those are signals, but all of the interrupts, all the signals, all of the system calls, a system call, open, close, human. So is /home, /my directory, whatever, human. Inode 10, 32, 69, 48, numbers. So anyway, initial conversion, access to the file is through the path name. Kernel needs to translate the path name to the inode to access the files. So there's a conversion table. The algorithm is called the namey. Parses the path name one component at a time, converting each one of the components into the inode list based on its name and directory being searched, yada yada. Eventually returns the inode of the input path name. So the dots, the double dots, the backslashes are all symbols. You give to kernel just step back one, step back one, step back one, and then the algorithm just goes back. The algorithm knows where it's at, and it just traverses through the algorithm. It's not using the names that you put in there. You're not even using those names. Because you could boot up the inode list, make symbolic links, and use different names if you wanted to. The blocks of storage are the blocks of storage. The interface to the blocks of storage is the file system. So it depends on how you want to get at the file system in terms of what algorithm you're going to use and how you're going to access it. So here's a typical naming algorithm. So if the file name is absolute, then it searches from the root inode. If it's relative, it's going to start at the current location. There's a pointer in the system in the tree. It's going to go to where it's starting from, or where you left off. last time you used the algorithm, and it's user by user, because you're the one traversing it. And it's going to take that pointer address and start or go back to the root, depending upon what you're doing. So the absolute, slower, much slower. You're thinking, well, it's just going back to the root. How do you really know where you are in the file system? You could be 2,000 directories deep. You don't know. You're going to go all the way back to the root of that server to traverse it. Not only is it a lot of work to type it in, but the algorithm is going to run slower. It's like the elevator going all the way over to the start of the disk to go find what you want at the end of the disk. Why go back to the beginning? So a lot of Unix people will just only use relative addresses for everything. Only absolute if you don't know where you're going. You don't know, then you use the absolute. Or if you have only access to a particular spot and it's not in your tree, but it's way over there, but you have access to it, then you use the absolute direct path to it, because you can't get to it from here, because you've got blocks, you have blocks, roadblocks in the way. So then that's where you have all the science that goes into what path name you're going to use, and how many people really think about it. Nobody thinks about this stuff. Not really thinking about how long it's going to take, because the speed of the processor is so fast. It does take longer though. If you actually do a speed test, you'll see the absolute will always take longer. Alright, so relative, starting from the inode corresponding to the current working directory of the process. Keep in the process U area, the user area. Let's see. So the components of the path name are then processed from left to right. Each component, except the last one, should be either a directory or a symbolic link. So the guessing game doesn't matter. It's all files, but we know it's a directory because we see the symbol of the backslash, forward slash actually. So, and we got the working inodes. So you're technically using the term working. You're in working inodes wherever you are. As soon as you've logged in and you have your inode selection and you start traversing in it, then you create your working inode, and then from your working inode you have your relative position, and then you can go back and forth. So if the working inode is a directory, current path name component, it's looked for in the directory sequence of the working inode. So it doesn't start anywhere else. If it's not found, then it goes recursively through the numbers, so it finds the location that you're looking for. And then that's a recursive search. So if you're at the current directory and you got 12 subdirectories, you're going to search through all those 12 subdirectories. So most Unix people that really, they spend a lot of time worrying about this stuff for some strange reason. You have one directory, then you have another 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 directory, you have another directory, then you have another directory. You're like, why don't you just put it all at one level? If you put it all at one level, you got more stuff to recursively search through. If you put it at one, each one of them has its own level, less searching. Because you have your relative location, nothing else, you're in a tree structure, nothing else matters. Which is the exact opposite of a FAT system or an index system. Index system, it doesn't matter. It's all got an entry. Inodes, it does matter, because all that other stuff's gone. You're just talking about where you are right now. You're just working inode list. This is what you got. So why are you going to have 100 files in this thing? You're not going to, or all these subdirectories. Which is kind of interesting because it's kind of mimicked in Windows. We get my documents, my pictures, my whatever, and then you got, program files, and you got, really, in the old days, we all just had one directory called C, actually it was the C drive, and everything is just on the C drive, and then around XP or so, they go, oh my, everything now. It doesn't really matter, it takes the same amount of time, because you got to search through the whole disk anyway. So anyway, searching's different because at the level, you don't want to recursively search through everything. Put everything on a flat level in an inode list. You're recursively searching everything constantly. It's like taking a tree and cutting it off and making it into a list instead of a tree. You're going to go through the entire list looking for something. So anyway, it's more efficient. So that's why you see all of these different subdirectories. Other concept I forgot to mention is we have no concept of drives. Mounting system. So the drives are mounted. In Windows, actually when I said C drive, I went, oh, I didn't talk about that yet. C drive, D drive, F drive, E drive, J drive. I don't know. Actually, you can only have 26 drives. Let's go double D, double A, double B. And then the drives meant something like floppy disk or CD-ROM. Do they mean anything anymore? I don't think they mean anything anymore. We still got drives. Because this disk has a fat system on it. This disk has a fat system on it. You actually went to the different disks. You click on the C drive. If the C drive is not working, it gives you an error. Oh, no problem. We go to the D drive. Oh, D drive's gone. There's no disk in the D drive. Okay, we'll go back to the C drive. We're on islands of our own. D drive doesn't know about the C drive. C drive doesn't know about the E drive or whatever drive. All partitioned out, all on islands of our own. No file sharing. I know it's no partition like that. We can still partition the drives, but we don't have drive abstraction. That's the biggest thing people have a problem with when they install Ubuntu. They go, oh, I'm going to switch over to Unix. And they stuff the disk in there in a little USB drive, and they go, where is it? Well, now we have a fake icon. It shows up with the mounting. It's generally MNT mount, and then it'll be S, whatever, HDA, whatever. You know, it depends on what type. Is it solid, whatever type of media you're looking at. And it'll say 1, or 2, or 3, or 4. Well, that's the inode entry showing you the entry point for the mount position of that disk. It's not a separate drive. So it's all part of the same system. Everybody belongs together. It's one big happy family. No separation, no islands of their own. Windows people are all in an island of their own. So, which is actually kind of interesting when you think about it. All those drives are so separated. Which probably is, when people start looking at file systems in Unix, that's the first thing you notice. Where's the C drive? Where's the D drive? So anyway, once you get used to it, you go, oh, this is so much more powerful. I can take 5 or 6 different USB drives and put them all in there and save stuff on different stuff, and it's all together. It's not drive 1, drive 2, drive 3, drive 4. All my music files can be on all of them. You're probably not going to do that. You're probably going to want to buy one big one, probably, but you could use 20 different little ones if you wanted to and have the same abstraction as having one big one. So, which is how you get big internet. You know how many computers there are on the internet? I don't know, there's some stat about how it grows every year. Servers being added and added and added, which is actually kind of cool when you think about it. But one of them goes down, do you really know it? No. Somebody goes away, you don't know it. It's hard to tell until you get, oh, inaccessible. Oh, okay. We'll go to another one. We get what we want. Or if you're Google, you got a whole server farm. Why did I tell you this one is like the old days when you had crops? Now you gotta take the crops away. You got servers, server farm. Got 25,000 servers or whatever. I don't have that many servers. I don't know how many servers they have actually. I shouldn't quote that. But and then you need this one breaks, take it out, put a new one in. They're just numbers. They have nothing to do with data storage. Your files are never going to get lost from your Gmail account. Actually, all of us have files in Gmail if we're using Gmail. They're all on different servers all over the world. Actually, some of my email is probably on one server, and some of it's on another server. Some of it's on another server. By the way, Gmail recently had a sync problem. You guys are familiar with this? Some people lost email. Did you lose any email? Anybody experience that problem? They had a sync with a bad server, a couple of servers actually, and some of your archives were mismatched because what they had to do is take it out, put another server in. They lost a lot of data, and then they had to resync it. So some of the changes that you made, some of the files that you put over were either misfiled because they had to restore a backup. So they're either misfiled or the archives were messed up. Like the archives went away. You know what I mean by archives is when you make a directory. So some of the archives were lost, and it didn't happen to everybody because it depends on what server you're on and where is your stuff. But some people had like parts of their directory. This was like a couple weeks ago. Some people had like parts of it missing, parts of it with different names, or the names were messed up, or the stuff was mixed around. It was all in one folder instead of the other ones. They try not to lose your data, but when they don't sync it correctly and it doesn't get synced because there's a failure in the system, there's a bad connection or something, and the stuff can't get synced, what's going to happen? weird stuff. So it didn't happen to everybody. It only happened to a couple 100,000 of users. And it didn't happen to your current mail. It happened to your archives, which is actually kind of interesting. So, well, from what I heard, I don't know. There's always weird things. You always know when they're doing a backup or a recovery or restore of some sort when you get them emails twice. Yeah, then you know, oh, wait a minute. How come I have 3 of these emails? How many times you sent? Just once. But it came in 3 times. Server reset itself. Recovery mode. But it didn't happen to me. It only happened to somebody else. Mounting file systems is what I was mentioning before. I think we are getting close to the end of this, don't worry. When the user started, directory hierarchy corresponding to the file system location, I assume that this is called the root device. There is a root device. On every server there's a root device. Because you gotta put the starting system, you gotta put the kernel somewhere. Kernel's gonna be on the hard drive. You're gonna have a root device. You have the mount utility that allows the super user to splice the root directory into the file system, into existing directory hierarchies, and the file system is created on other disks that can be different locations. So different types of disks, which is the cool thing now, actually. Now they have these utilities, I can't remember what it's called. They make them for the MacBooks, actually. A special kind of drives where you can put multiple drives in the system. Well, they're using it for clouds, actually, but you put multiple drives in, it makes one big drive out of the whole thing. And it's the software abstraction, and I can't remember what it's called right now, but it makes the architecture to be read as one drive. So it's multiple arrays of drives. It's not RAID, it's something else. It's something brand new, actually. A lot of the clouds are doing it. You get a Fry's and you buy your own cloud. Actually, I'm seriously thinking about doing this. I've seen them, they're pretty cheap now. You can buy like 30 gig or so, or no, I'm sorry, 300 or 400 gig or so. Depends on how much you want to spend on it. Cloud boxes. So it's got a low energy consumption, quiet fan. You stick it next to your router or your server, and it's your personal private cloud. So you can keep that running all the time. Instead of putting your stuff on Google Docs, instead of putting it on the internet, it's private instead of public. And the software that runs on it takes, you can replace it, you can upgrade them, stick more disks on there, put solid states with regular older drives, yada yada. And the software that runs it makes an abstraction of all the disks and makes it into one. So you got like thousands of gigabytes of data available to you. You can use it for backing up instead of using, you can use it for Google Drive applications, Dropbox, make your own Dropbox thing out of it. It takes it off the public internet. My biggest thing is if you put something on a cloud, you use a public interface, you're on the public internet, the public has access to it. And you're thinking, who owns your data? Somebody who's housing your data owns your data. Why not put my own data in? So you don't even have to put your own server up anymore. You could easily put your own Unix server up or your own Linux server up, but you don't even have to do that anymore. Just buy one of these little cloud boxes. Plug it in, and it doesn't burn up too much energy, and it just sits there, and you have all your cloud over there. So I'm thinking about doing that and getting rid of bhacker, because it's a GoDaddy website. So who's got my data? GoDaddy. So instead, put it all in the cloud. Students go into cloud, and you want Unix server, cloud. Log into that sucker, hook it up with a Unix front end. I don't even have to use Amazon anymore. Just stick it all in my cloud. You're logging into a cloud. I mean, it's just Amazon servers with a Unix-based operating system. Actually, it's probably Ubuntu. So I'm thinking is on that. So anyway, in the old days, you had to like have your own like whole big old computer set up, put all your software, your server on there, and install everything. It's just easier. You just buy it, store, get a store, buy a cloud, bring it home, plug it in. Now I don't have to use Google anymore. I just have to figure out an alternative for Google. I want to get off of LinkedIn. I want to get off of Google. So those are my 2 goals for this year. My New Year's resolution: get off of Google and get off of LinkedIn. I'm not going to go because I'm being recorded. When I stop this recording, I'll tell you about LinkedIn. All right, or Google's public. LinkedIn is probably a little bit not so good to talk about. All right, so when mounting establishes the user is unaware of the cross points that are going on. You don't know who else is mounted in the system. You only know your entry point. For every mount, there's an unmount. get rid of it. So here's a mount for a floppy, a device floppy, which is going to be the driver, and the mount point, which is going to be MTN. So it's either mount or MTN is very popular in terms of that. So floppy, USB, there's different device drivers that are used in correlation with the mount to mount it to get different levels. Actually, you can actually add the file system, the -F flag for file system, or -F, and then you go NFS or something, and then you can mount it with a file system. You can actually take the same disk, mount it with different file systems, and put the same, have different file systems on the same disk, as long as you're going to different entry points for different partitions. So it's actually kind of useful. It's more flexible than you get in Windows. You have a Windows disk, and a Windows operating system, and you load a USB disk in there, and there's two partitions. There's one that's a FAT, and there's one that's a HFS plus. You're only going to see the FAT. You can't mount them separately. As two separate file systems, it doesn't work. Actually, you can't put HFS plus on there at all. So now the cards are turned. See, in the old days, people that had MacBooks were on islands of their own because they couldn't read Windows files. So now MacBook can read Windows files, but Windows can't read Mac files. Which is kind of ironic. It's just switched around 100% in the opposite direction. Now Mac people are more flexible than Windows people. Then what is the other way around? So. Alright, so kernel maintains a system-wide data called the mount table. We have a mount table, another data structure that the kernel has to keep track of which devices are mounted and where they are in the mounting system and the hierarchy of the inodes. Multiple file systems can be accessed via the single directory hierarchy. We have mount and unmount system calls that are used. So here's our mount. If you have a USB drive, you could log on to the Amazon server and mount your USB drive into your student account. And after lunch, I'm going to try to do this. I have to go find a USB disk. I think I might have one in my bag somewhere. I don't know what format it's in or what condition it's in, but I carry them around so I can do stuff with them. I'm going to try and mount one up so you can see it live. Probably not till we take lunch. Actually, I'll do it in the afternoon. But you can see you could actually mount your disk in there through the telnet connection and actually have access to it, which is I think we're going to have to try and hopefully do. And you're wondering, well, how in the world can I do that? I didn't bring my disk and take it over to the Amazon server in Colorado or wherever it is. No, but you have the abstraction so you can read and write to the disk through your telnet session. This is going to be part of your directory structure. So we'll see what happens. I'm going to try it out, see if it works first. And if it does, I'll show you how to do it. You don't have to do it. But let's say you wanted to copy all the stuff that's on your UNIX drive and you want to take it over. Probably easier to FTP it, or you can mount a disk in there, copy it onto the disk. Doesn't really matter. It also depends on what security is set up. You may not have access to mounts or unmount. Actually, I could test real quick. All we have to do is type in mount. Let's see. Let's see if mount's going to give me an error. Nope, it doesn't. Look at that. So I possibly will be able to get it to work. So we'll see what happens with that after lunch. But all right, so what are we looking at here? This is the mount command. So you mount with entries added with device number containing the file system. So we have device numbers. That's where you get SDA1, HDA1, 2, 3, 4 is the name of the symbolic location where you're mounting into using the device driver for a hard disk or solid anyway, the disk type. So a pointer to the root inode to the newly mounted system, a pointer to the inode and the mount point. There's a lot of information being sent to the kernel from a mount. So a mount is a system call, by the way, as well. So it's a lot of information to create the directory structure. The unmount does the opposite, takes it out, cleans it up. When you unmount, you can actually remove the temporary memory that's associated with it and then write out any changed content to the disk at the same time. So it checks for any open files, flushes out the superblocks and the buffered inodes and things, and cleans everything up, removes the mount table entry so it's no longer there, so you don't try to write to it. What ends up happening is people mount something in there and then they remove the disk. It doesn't remove the mount point, and then they start writing to the mount location. but the disk is gone, and then there's no error, nothing happens at all. Those turn into lost clusters eventually because there's no home for them. They're lost. You can't write them anywhere. So process states. So the process subsystem, going back to that concept, has different states. We saw the states. This is a little bit of a review at this point because I've already gone through this. We have the running, the runnable. If you're not familiar and you can't remember all of the different states of a process, here's some examples. This slide's got 6 of them. The Android operating system, when we were just talking about embedded Android earlier, has the process concept, and all the states are written in the application development. So if you take the Android class, you see there's the on create, on resume, on suspend, on destroy, on all that on stuff. Methods is the process state. So instead of the kernel, this is the weirdest thing about, they take a Unix system and then they modify it. That's why I say Android is not Unix. It's modified Unix. Instead of the kernel being responsible, because the kernel is way over here, working on your phone service and stuff, instead of the kernel also being responsible for the running of the process, you're responsible for it. So you get free reign. You just load it up. And your process is in control of itself. So on resume, on the start, on the end, on the pause, all these different states, it's the process state. You can clean up your memory. You can put something in the background. You can check for something. You can restore some data. And they have this thing called intents. If you've taken my Android class, you go from one activity to another via an intent. That's a pipe. So it's a Unix pipe. So you take the pipe, turn it into an intent. What does the intent do? It sends a bundle. It's a bundle of the data that you're sending through the pipe. But it does it for you automatically. You don't actually have to put the bundle together. You can put some stuff in the bundle, like name is this, password is this. Okay. And then what are you doing? You're redirecting your output through a pipe to the receiving process, because you got one process, two process. In Android, they made it simple. Only one process runs at one time, which is the most bizarre thing. And then on any motion state, the process ends. So then you go, oh, my app just ended. You know, on bad apps that don't work right, you're in landscape, you go into portrait mode, and oh, it ended. It doesn't happen as much anymore because people are like, oh, that's kind of stupid. Why don't I just fix it? You're supposed to, because it's on destroy, the process is going to get destroyed because the OS is going to reorient the interface for you. It's going to reset everything for you on the user mode. Everything just shuts down. Not so good. So, because the app itself is its own process and it's supposed to keep control of itself through all of these different states here, you actually have to go, okay, on destroy, start me back up again, or whoa, on rotate. So they built some facilities and some system calls in to say, if this event occurs, then do this. If that event occurs, then support this. So then you have to tell the manifest to kind of control what happens with the process. Because the manifest is sort of your system call interface kind of thing that goes on. So I don't know why they call it a manifest, but anyway, you don't have to know anything about Android. But what I'm trying to tell you is that they modified the process concept to simplify it and put more control to the user instead of the kernel. So in Unix, kernel keeps track of all these states. The user doesn't care. The user just wants to use their program or close their program from a process perspective. Android is the exact opposite. Kernel doesn't do anything. User does everything. Programmer does everything for that app. So, right. Examples of process states. We got runnable. So when the process issues an I/O command, it becomes suspended and then becomes runnable. That's interesting, runnable. And then when the I/O completes, it will run depending upon the priority. Process completion, composition, excuse me. We've got the 3 areas of a process. Normally they draw it out with a rectangle box and they cut the box into 3 sections and they put heap on the top and stack in the middle and code and data on the bottom. And then this is operating systems, if you remember operating systems class. I'm not going to go into that level of detail, but know that Unix is this is where this came from. So if you remember anything from operating systems course, if you've taken that before, the code, the stack, the heap, the code, the data, that's what you're looking at. That's in the process memory that's stored for each one of the processes. And not part of this course, but part of a basic operating system course. But it all comes from Unix. The user area it's the private user area that's for the housekeeping information. So it's used by the kernel for the process memory. So the user area is where their second stack is going to appear for the most part when the process makes a child process. Threads forks off another process. Sometimes the user area holds into that information about the second process that's in there, or second thread that's in that process. Controls the control and the status information. Contents of the user area can only be accessible when the process is executing in the kernel space. The user never gets control over it. Which is why once you create a child, you're done. You just sit back. If you're the parent, you just sit back and wait because you can't do anything. You're frozen solid because you can't access this area. But the child's in there. What's the child doing? The child's communicating with the kernel now. Okay, you just patiently wait for the child to finish and then send a signal back to you. I'm done. Oh, okay, good. Now I can take over again because it's going to lock your user space. And the kernel is only going to pay attention to the child, who's the who's currently running thread that has a stack executing. So we have different stacks. So contents of the user area can only be accessible. Okay, yeah, kernel can only access the user area of the kernel, of the memory area. Kernel doesn't access anything else, which is the weirdest part. It only accesses the user area, and user area is the code and the data. Kernel has no control over your heap, which is why languages like C++ create memory issues for kernels. Because a C++ programmer or C programmer can take and use alloc with no dealloc or no remove. It doesn't remove anything. Allocate, allocate, allocate. Kernel doesn't clean that up. So what does it do? It just destroys the running process. It fills up the running process. Whenever the kernel does, it cannot go and remove all that stuff you put in there. It has no access to your heap, only into user space. So that's what, if they could just fix that, give the kernel access to the whole thing, then that would solve the problem of memory leaks for C++. But there's a problem with that. If you're going to separate things out, when I mentioned originally, this whole dual mode concept is kind of a mystery in terms of how it's really supposed to work, because it's two separated islands. You can't put yourself on the same island. You do that, how are you going to run anything? You lose control as a user. And if you're the kernel, you got to open up yourself, expose yourself if you're going to keep track of the user's heap, because you're sharing now. There's no sharing of anything. The kernel works on its own island and the user's on its own island. So they don't communicate. The kernel receives information from the system calls, but they don't share any data. They don't share any memory at all. So you can't. So if you're going to do it, you're going to make it so that C++, the programmer can potentially create a bad, faulty process by not cleaning up its user space correctly, because the kernel's not going to do it for them. Alright, so important fields of user data. We don't necessarily need to go through all this, but pointer to a process table slide of a currently executing process is kept. File descriptors for any open files are going to be kept here. Internal I/O parameters, current directory, root structures, yada yada. And how much CPU time a process has recently used. That's an important one to keep track of. You want to make things fair, then you're going to update the process table with how much time has the process gotten. And if you have one process that's getting a lot of time, then you should be able to kill the process or preempt the process or maybe lower the priority of the process. If you're Windows, you don't do that because you have no idea about runaway processes because you're not using time or priorities. So then you got, well, I'm going to design an operating system that's going to have priorities. It's going to use time. So, long story short, that's a hard one to program. Because someone's writing this program and you have to think about, well, what's going to happen when the programs are running? And if you're Unix, then you say, well, let's just create different types of users. The roots is always going to have more processing time, more CPU cycles per their processes than the user is going to get any other user. Root's going to have everything. And then, you know, you're going to have different levels. So on a Windows system, admin has the same processing speed as any other user. So what does it matter? It doesn't matter. It's just different access to the disk, which is the funny thing. Originally in Windows, all users had access to the same hard drive. I don't know, can you still see other people's files from other different accounts? They just put in there my documents and folders or whatever that subdirectory is that keeps track of the personal settings for each one of the users. But isn't the disk the same? Yeah. Can you map it differently for different users? I don't think you can. I don't know. Which is different for Unix, because in Unix you can map everything. You're sharing the same disk, but you're not sharing the same files. You're not sharing the same user environment. And you don't even have the same access to the same kernel processes, and you have yours kind of kept separately. And then you can put multiple users on simultaneously. Does Windows support multiple users simultaneously? I don't think it can, actually. I think it's one at a time. And then you're using the entire disk. So you could technically touch somebody else's files from a different account, is what I'm thinking. I haven't been using Windows long enough to determine that, actually. But anyway, process table, talked about that earlier. It holds all of the information about the running processes. Process information, what we're really looking for is the ID of the process, parent ID, child IDs, the state of the process. It's real and effective user group. Processes have owners. If you put the group, the owner of the process is in a high priority group. In the group, then the process gets more CPU time and more allocated time because it's a higher priority. It's a priority system. So it depends on your group ID. If you just have one group ID, then there's no priority going on there. Location, its code, its memory address, all of its pending signals that are separated out per process, various different times, process execution time, kernel resource allocation, utilization, stuff like that. It's the scheduler. Now I've given you all this stuff, so I'm just going to show you the text slides for it. Schedulers, that's what I call the CPU scheduler. It's really referred to as the scheduler. It's the time that is allocated in the routine. This is another algorithm that's put into the kernel to basically make those processes run. So the scheduler is giving CPU time and I/O resource time to processes. Scheduling rules are put in there. Some goals are to make them fair. Unix doesn't care about fairness. Windows cares about fairness. Unix, we don't care about fairness. Background processes don't get as much time. They're not scheduled as often. They don't work the same way. I/O is treated differently than CPU time. Then we got this middle ground. We don't know what to do with this queue. Just stick you in there. We don't care if it's fair or not. We have starvation. We have race conditions. We have deadlocks. We have everything. It's survival of the fittest in Unix. It's fairness in other operating systems. But if you think about it, if you're not doing it right, then it is survival of the fittest. Get rid of the weakest threads. The poorest, weakest, lowest priority threads starve to death and die off. And we don't use them. Which is actually kind of funny when you think about the concept of life as a thread. There was a Channel 9, a PBS thing. It was actually kind of, it was for undergraduate operating systems course. I have it recorded. Don't have it available. It's on some disk somewhere. This was before cloud storage came into effect. And it was life as a process. It was an animation, a cartoon about different operating systems and different processes, and then went through. This was nice actually for undergraduate courses, or even for some graduate operating systems courses. Not really applicable to this class, but the process gets born, and then it gets into the PCB. And then the scheduler comes over and says, hi. And it puts it up into a memory bank and stamps its name on the memory. And then it's actually kind of cute. And then it comes back and says, would you like to run? Comes and visits this. The scheduler comes back and visits it occasionally and then updates it. It gives it an A, B, gives it a grade, you know. And it just updates everything. And then it comes back. And then finally, you know, you see the process growing. It's getting older. It's aging. And the kid's getting a little bit bigger. And then eventually goes away, and it says, rest in peace. It was actually kind of funny. So there's another one, actually, for networking, where the little packet gets on a conveyor belt and goes from router to router. The same guy, I have to find him, actually. He puts together it's one guy who does it. All these cartoons about all of these computer science concepts. It's actually kind of funny because you look at that and you never forget the whole big scheme of how the scheduler works, because, you know, and how the process ages, gets old, and then goes into the retirement home. Time at home, it gets faster processing speed because it's got more needs. It has to finish up. It's got an expiration time on it. Anyway, yeah, I should look for it maybe on my lunch break. Maybe if I think about it, we'll watch some videos not tomorrow. Tomorrow's Super Bowl. Not tomorrow, but the following weekend. So tomorrow you guys are going to watch it. I don't know what time does the Super Bowl start. 12?
12:30.
I'm going to lose you all tomorrow when you've been watching the Super Bowl on your computers. But we still have class, by the way. Anyway, we're going to get a lot of stuff done today because I know tomorrow's not going to be very productive. All right, so during so the scheduling rules, every second the process is in a non-empty queue, has the highest priority, is going to be allocated some CPU time. This is just blindly saying a round-robin fashion. Don't necessarily need to use round-robin fashion. If you take an undergraduate operating systems course, you'll learn about first in, first out, last in, last out, first, all these scheduling algorithms. So, schedulers have support for real-time processes, and scheduler needs to change so that the scheduling is based on priorities. So we have a priority-based system. Inheritance rather than time quantum. Preemptive points of the kernel are needed as well. Yeah, this whole thing is called context switching. Context switching is the kernel memory switching from one process to another. It's actually referred to as the context, and we switch it when we go between different processes. When we load an executable file, we just make the process, and we create the thread at the kernel level, and we schedule it. So the user compiles the source code. We have a set of headers that describes the attribute of the file. This is the interesting thing. So in Unix, it's all about the header. In Windows, it's all about the file name. If the file name says it's executable, then it must be executable, right? In Unix, we don't care. We have output, a.out, which actually comes from the A language. We have B, then we have C, which you're using today. But we still got a.out. Still the same output. So a.out. So what is the output when you run it? You see the output. Well, long story short, there's a header in there. Even if it's binary, there's a header. You write a Perl file, there's a header. PHP, there's a header. Python, there's a header. All your Unix scripting languages have headers on the top. So that the interpreter knows what it is, so it knows how to interpret the instructions correctly. It doesn't matter what the file is called. File name has nothing to do with it. So we have program text, machine language representation, and then we have symbol tables and stuff like that are in there. So we have the text, the data, and the stack that are created from the executable files loaded up into memory. So I'm going to stop. Let's see what time it is. Yep, I'm going to stop at this point. A little bit, there's a couple slides or so left of this lecture. I'll cover them next time. Or after lunch, I should say. Next time I lecture. But I think this is long enough, so I'm going to stop this one. I see a lot of tired faces.